we have to draw the original graph. So sketch the graph. So we're going to graph f of x. So we know that the domain is 0 to infinity. So when we sketch our graph, we only want to consider values that are to the right of the y-axis. Okay, that's a little bit helpful. And we're also given a point, 0, 0. So we might as well plot that so we have a reference point. We also know that we have a vertical asymptote at x equals 3. So let's draw that in 2. So we'll have something like this at x equals 3. Okay, now D through H looks like we're going to have to interpret what these things mean. So A through C was just to get us going with some reference points. All right, so D and E are telling us something about the first derivative, and so is H. And then F and G are telling us something about the second derivative. So what we're going to do here is we're going to try to make a little chart before we try to graph this thing. So we're told that the first derivative is greater than 0 when x is less than 1, and it's less than 0 when x is greater than 1. So what that means to me is that, well, look at H. H says that f prime of 1 is equal to 0, right? So that means at x equals 1, I have a critical point. Similarly, for f and g, I have my second derivative changing sign at x equals 3. So it looks like x equals 3 is going to be an inflection point. Now I'm seeing a slight contradiction here, right? The domain is saying 0 to infinity. I think the domain here really should be this. Because if you have an asymptote at 3, we have to be super careful. That means x equals 3 is not an inflection point, because an inflection point has to be in the domain. However, at x equals 3, we're still changing concavity. We just can't classify it as a inflection point. So yeah, there was some kind of contradiction between these two, but we're good. Okay, so let's make a little chart here to see what's happening. So things happen at 1 and things happen at 3. So let's care about those guys. So here's 1 and here's 3. And let's get what the first derivative is, the second derivative. From there we can figure out the shape. That'll be enough information. Okay, so when x is less than 1, this is where we are. So that means my first derivative is positive. So that means I'm increasing up to 1. And then when x is greater than 1, we're told that the second derivative is negative, which means we're decreasing. Okay? Same thing for x equals 3 with the second derivative. So up until 3, it looks like our second derivative is negative. So that looks like we're going to be concave down up until 3. And then once we're greater than 3, our second derivative is positive. So then we have concave up from there. So now we can put these two shapes together. So if I'm increasing concave down, I look like this. If I'm decreasing concave down, I look like this. And then decreasing concave up, I look like this. So now we just go to our graph and we're going to add all of those pieces in. We don't have to be precise on the y values. The only real point we were told is the 0, 0 point. So here's 1, here's 2. So from 0 to 1, maybe we just have something like that, right? Just taking that directly from the chart that we made, right? Now from 1 to 3, we have this guy here, and we have an asymptote, so why don't we just connect what we just drew and draw in that shape that we have to be something like that. We have an asymptote, so the behavior towards x equals 3 is expected to just follow that asymptote. So there we go. And then right after our asymptote, we have this shape. So it probably comes from the top of the asymptote like this, and then just does something. We don't know what it does over here. All we're concerned with is satisfying A through H, right? So as long as we have that, we're good. So it seems like that's all we had to do here, and we've answered the question.